welcome back. I hope you guys had a wonderful break. We have 4 more lectures, 4 more classes scheduled, and I wanted just to go over, what's going to happen on those 4 classes. So we have Monday, Wednesday, and Wednesday. The final exam is Monday, December 15th?
15, yeah.
I don't remember the time except for the fact that it's very late at night. 8 o'clock?
8 o'clock?
I'll try not to snore when I fall asleep around 9:30. Okay? Wednesday, or rather a week from Wednesday, which is what, the 8th? That's right. Wednesday, December 8th, we have a test on the homework and the project. Okay? And what, just so you don't get confused, there's going to be it'll count for 30 points, so there'll be 3, you'll have to answer 3 or 4 problems. Let me think about it. I'll just be clear. You will have 1 required homework problem. You will have 1 required problem on the computer project, and then you'll have to pick 2 out of 3 problems from homework. Okay? So there will be some choice and some not so choice. Okay? And then the homework problems will be all problems that I've assigned out of both Bolanis and out of the small thin book out of Slater. Okay? So that'll be here. There will be no class on Monday. I'm out of town, and so I've decided to give you a study day. Okay? I could tape a lecture, but I figured I'd just give you a study day for that. Okay? And then we're going to look at antennas here and here. But really what we're going to be doing is Huygens approach or spherical waves. And where we're really going with this is our types of antennas: horn antennas or phased array antennas. Okay? So we'll talk about it as if it were an optics problem, and it is. The elements that we'll do is an optics problem. But a more general classification is that these are waves or antennas that are analyzed using superposition or a sum of spherical wavefronts, and in particular, the diffraction grading example that we do is an example of a phased array antenna. Okay? So I don't want you to think that, because I cast it so narrowly in optics, I don't want you to think that it's really only an optics problem. The more RF microwave approach is these fabulously expensive, fabulously flexible phased array antennas that pop up in a lot of very critical situations. Okay? All right. Any questions about the schedule? Okay. I'll send out an announcement to remind you about Monday on e-learning, and also an announcement to remind you of the test, the homework test as well. And I'll certainly do that if someone sends me a quick reminder at the end of the week to do that, because I am forgetful. Okay? All right. Now, at the end of if we go back ancient history, like before Turkey, before the Cowboys' horrible loss, we saw that we were looking at this half-wave antenna structure. Okay? And we did all this wonderful mathematics, which I hope you thoroughly enjoyed. We got the full solution, near field and far field. Exploited symmetries to come up with the integrals that we really couldn't even do very well at some point. And if we step back at the end, what we found was that the output could be characterized as not a rod of an antenna, but rather three edges to the problem. Three edges to the problem. The tip of one metal wire, the tip of another metal wire, and the center. And if we replaced the metal wires as just sources of spherical waves at each one of those points, we got exactly the same near field and far field solution for the electric field and therefore the magnetic field. Okay? And that's what Huygens taught us in the 1600s. So back when is light a particle or is light a particle or a wave? Well, Huygens was very clear that electromagnetics and propagation, all this was all about the spherical wave construction. Okay, and again, it's very similar to, I think I used this analogy last time. If you have this antenna can be replaced by dropping a stone here in water, a stone here in water, and a stone here in water, and watching those wave fronts migrate out and look at the constructive and destructive interference of each of these waves as they hit a certain observation point. And I want to build on that in tonight's and Wednesday's lecture, and we'll call it diffraction and leading into diffraction gratings. But again, my goal or my motivation is to sell this to you, to describe this to you in an optics world that you may be familiar with, but also point out that this is also exactly the mathematics that leads to a phased array antenna system. Okay? So, if I start with a point source, if you think about it, all sources are far enough away are a point source. The sun looks like a small point source if you're far enough away from it, even though it's tremendously complicated on the surface of it. The disturbances that come out from this spherical source are phase fronts where the same distance is in the x, the same distance is the y, the same distance in the z, propagation a foot a nanosecond in the x, a foot a nanosecond in the y, a foot a nanosecond in the z for my retardance time. And so the phase fronts build up as spheres. So if I freeze time, I see maxes, mins, maxes, mins, maxes as I slice through an orange or a sphere. Okay? The radius of these phase fronts gets bigger and bigger as I move further away. The number of nanoseconds times a foot a nanosecond, the speed of light, is a bigger number as we march through in time. And so the phase fronts that started longer ago, that are further away from the source, have a larger radius of curvature on it. If I keep going, eventually I get a radius of curvature that is so big that they might as well be plane waves. So a spherical wavefront, or spherical source, when you get very, very far away, infinitely far away, but to an engineering approximation, just a reasonably decent distance far away, you get, lo and behold, that's where plane waves can come from. Okay? If you perturb this by sticking in a metal piece or metal plate or some edge on this, then you'll get a diffraction, and you'll get a new source of spherical wavefronts. And so you may start at some origin, at some spherical wavefront. There'll be a propagation from that origin out to some spot, some surface, R0, and the phase of the wave all along this sphere will be the same. That's what we mean by a spherical wavefront, is that all the photons or all the disturbances along this arc were produced at exactly the same femtosecond. So if there's a disturbance at some point Q, then there's a possibility of a scatter along a line S to an observation point P, and we'll call the angle between the original arc R and the new path S is chi. And so what we'll write for the disturbance is a differential U of P, which is equal to some cross-section scattering, which is a function of chi, times the spherical wavefront times the new phase front, or the new scattering center, over all ds's. So here's my original spherical wave, and here's a new spherical wave from Q. Okay? So you recognize the e to the ik over s, e to the iks over s, and e to the ikr over r. Those are spherical wavefronts. The complex exponent are the sinusoids up and down, and the 1 over r dependence is the roll-off, the peanut butter over the basketball that I've been talking about again and again and again. And this is called, if you're looking for a word, the Huygens Fresnel construction for one differential disturbance moving towards a propagation point P. And what we want is we want the total, not the differential du of P, but we want u of P. So to do that, we have to add up all the contributions of all the new spherical wavefronts that see a perturbance at all the various values of Q. So what this tells us is, in accordance with this scattering function k of chi, we smear across some aperture a whole new array of spherical wavefronts. And we let these spherical wavefronts propagate to some observation point. weighted, W-E-I-G-H-T, weighted in amplitude and phase by the cross-section K of chi. Okay? Now, the terminologies become a little bit different. If you're very, very far away, if this S is very, very far away, the observation's at the infinity plane, then you do something called Fraunhofer diffraction. More generally, if you're interested in near field effects, you do Fresnel diffraction. Okay? So we looked at far field and near field. Well, when you talk about diffraction theory and these kinds of integrals, the names become different. Fraunhofer for far field and Fresnel for the near field. Vocabulary is not that important. I just bring it up in case you want to, find out more about it. So we'll do a little bit of Fraunhofer diffraction, and that's far field, infinity, in fact. And we'll do a very simple disturbance. Sure, sorry. We'll use a very simple disturbance where we'll have a waveform coming incident on a structure, and the structure will just be mostly an opaque shield with just a very small gap in it. With just a very small gap in it. And this will be the famous single slit. Okay? Now, one trick, so what we'll do is we'll ask, what is my observation point at infinity? But one very simple trick we can play in the optics world is to move infinity up to a certain plane by using a lens. So if I go in and I put a lens right in front of that aperture, and a lens with a focal length f, then whatever happens at that aperture will happen at a focal length f instead of at infinity. Okay? Again, that's not necessarily a huge trick, but it's something that I'll just talk about a little bit as, in the context of an implementation of this. Because who wants to wait for infinity? Right? So you can move infinity closer by imaging and using a lens. Okay? And it's no coincidence that that lens would be called a Fourier transform lens. Okay? So 0 is in the center. We'll have S equals 0 in the center. The top of this will be b over 2. The bottom will be minus b over 2. This plane here will be the S plane from this integral here. So S equals 0, S equals b over 2, S equals minus b over 2. And what we need to do is we need to weight, or we need to smear this aperture with a bunch of spherical wavefronts. Each of these spherical wavefronts radiate out, and at some observation point, P, have the superposition of this wave, this wave, this wave, this wave, this wave, this wave, and all the other ones smeared across the aperture. All the constructive and destructive interferences will add up at P to give me some net amplitude and distribution. If I'm at some point S, that spherical wavefront will move towards P as well. So this distance will be x. This distance here will be a little bit longer. It'll be x plus delta. And that delta is given by the relative distance there. Actually, I guess this would be minus delta, and the one from below it would be a little bit longer, and that would be the x plus delta. Okay? Now, this is a very, very powerful technique because it's very easy to do this integration. It's very easy to if not analytically, then certainly numerically. And you can imagine anything you want in this k of chi function. So we'll do the simple case where it's a plane wave in, so there's all uniform spherical wavefronts that all fire in phase. But you can imagine that doesn't have to be that way. If I came in at an angle, if I came in with a plane wave at an angle from below, these guys would fire ahead of these guys. So if I adjust the phase, I'm going to steer the beam. I'm going to steer the output of this aperture. And I could also come in with more light on the sides than in the middle, or more light in the middle than on the sides. Okay? So I have a lot of degrees of freedom in here, and that's modeled exactly in this K of chi. Okay? How you weight W-E-I-G-H-T, each one of these spherical sources in amplitude and in phase. Okay? So we'll do the simplest example. All right. The differential disturbance, du of P, will be some amplitude multiplied by some ds over x, and then the sine of omega t minus kx. And that will be the disturbance and the center, from the center of the aperture. And then from an arbitrary position along the slit, I just have to add a little phase term inside that sinusoid. Now, the phase shift is this piece right here. So K times delta is equal to Ks times the sine of the angle theta. So delta is equal to S sine theta, multiply through by K, and that's Ks sine theta. Start to see a lot of similarities between the center-fed antenna and this piece here. Now, to build on a little bit what we had before, oh, hang on, one thing. Something that was a little bit wrong here. this denominator should be an x plus delta. But if we're in the far field, what do we do with that delta? We kill it. Why? Because it's small relative to the x. Okay? So the delta matters in the phase. It doesn't matter in the amplitude because it's so negligible. And that's what we mean by Fraunhofer diffraction in the far field. Now, I can also do a couple of other things. In our problem, A is not equal to A of S. So it's constant. The magnitude of each and every one of these spherical wavefronts is constant as I move along the slit, the opening of the slit. So by writing this, I'm reminding you that your problem may be much more interesting. Okay? And then the other thing is, there could be a theta of S here. So there could be an additional phase term for each and every one of these spherical wavefronts. The wave coming in at an angle, for example, or the feeds of that antenna being purposefully phased differently. In which case you would put in an additional phase term into all of these sinusoids. Okay? So just again, showing you how you might generalize the problem, because it is so powerful. And then, in the same way that we looked at the center-fed antenna, we had sources above and below at S and minus S that we paired together so that we could do these integrations. So in pretty much a review of what we did the last couple of lectures, except with tremendously different notation and tremendously different interpretation, I can write contributions from pairs of S's. So this point here is at positive S, there's another point here at minus S, and these lines, the x plus delta and the x minus delta, add up in this way. We note that the sine of alpha plus the sine of beta is equal to twice cosine alpha minus beta over 2 sine of alpha plus beta over 2. Trig identity. And so this expression here looks like that, where I have the original propagation term, and then I also have the phase term sitting out front there. So U of P is the sum over the slit from 0 to b over 2. We just have to add up half of this because I'm taking below and above the origin. So just substitute in. And again, you can see where we might include a phase term, an additional phase term in here, or an additional amplitude modulation here. I don't think I need both of these DS's. So pull through the integral all the things that are not a function of s. So notice that I have this factor here, and I'm evaluated between s equals 0 and b over 2. S equals 0 goes away. Sine of 0 is 0. So this is just equal to and what I'll do is I'll multiply this expression by b over 2, and I'll divide it by b over 2. That cancels with that. And notice that I have AB over x times the sine of KB over 2 sine of theta over KB over 2 sine theta. And then I have my propagation. So this is now in the form of a sinc function. And I'll write all this stuff in here as beta. Remember that. That's going to come back again and again and again. So beta is equal to k b over 2 sine theta. And then that's sine of omega t minus k x. And the intensity, this is the field, so the intensity is going to be proportional to u squared, or proportional to b squared, sine squared beta over beta. And if I plot that, pi, if I plot this in beta, 2 pi minus pi, and so on. I see the familiar ringing of the sine x over x rectified. So this beta, the decay of this goes as 1 over beta, and the zeros roll off as 1 over beta, and beta also implies the zeros, where the nulls are and where the maxes are. Okay? Now, if you look at our initial problem, we had a slit, and the slit was infinite in this plane coming out of the paper. And if we went to the far field, i.e. at infinity, the pattern was not a uniform distribution of radiation across the aperture, but it transformed into the sine of x over x behavior, or sinc function. And if you remember, the Fourier transform of a square pulse is a sinc function in the frequencies domain. So this is a naturally occurring example of a Fourier transform. And again, you have to wait for that Fourier transform all the way at infinity. But if you drop in a lens, you pull that infinity up to the plane of the focal length of the lens, and you have your sinc function at an accessible distance. Okay. So that's kind of an interesting situation. And by the way, we didn't do any Fourier transform. We didn't assume any Fourier transform stuff when we worked through this. Okay. Now, let me change the problem just a little bit. Supposing I have a slit, and I'll draw an axis through the slit, and I'll call an S here. And this source here, by the time it gets to the slit, will be a plane wave. And so I'll set up my sinc function sitting out over here as the transform here. So this will be a plane wave across it here, and it will go out to a plane wave there. Now supposing I have another source close to this, and it's going to come through the slit almost parallel, but not quite. And this angle will be alpha. And not too much will happen. It'll spread out a little bit. It'll be a little bit off. But what I'll have is I'll have a sinc function sitting out over here. So what we have over here is going to be the superposition of the two sinc functions and the question is, as alpha goes small, as alpha decreases, what's the minimum alpha where that I can resolve these two peaks? And it turns out that that's going to happen where pi, remember these are separated out by pi's, and if I put in what k is, 2 pi over lambda, I get a lambda in there. If alpha is small, I'll get pi b alpha over lambda, or alpha equals lambda over b. So again, we have a lambda over b relationship, like the lambda over dl relationship of our dipole. This one has a very different interpretation. This is called Rayleigh's criteria for distinguishing two sources far away from the slit in the far field of the slit. Okay? So how can you resolve with a finite aperture two different sources? Now, the application that Rayleigh had in mind were two stars very far away. Stars very far away, observed by the same telescope, the same aperture of a telescope. What is the minimal resolvable angle that you could see and separate out one star from another star? And so one star images off to this blob, the other star images off to this blob, where those two blobs can be resolved. The minimum one is when that angle is lambda, the wavelength you're observing it at, divided by the size of your aperture. So as your aperture gets smaller, the angle gets larger. So you need very, very, very big telescope optics to be able to see the differences between two stars sitting way out there. But this also works for semiconductor mask making as well. If you have two lines on a mask and you want to project them down onto the silicon, well, you need a large stepper lens, and you need to be working at very short wavelengths. Okay? Same is true in a microscope. If you're trying to see, to find out, resolve structures within a cell. Working at shorter wavelengths, you don't want to kill the cell, so that limits what lambda you use. And you want to use large optics to be able to see those. So this is a really general resolving criteria all across the spectrum, all across scales for RF, microwave, and optics in terms of resolving features. Okay? And You can say, if you want, that it rests on Fourier transforms, but the Fourier transforms is really just a consequence of the physical construction of Huygens and, as we learned a while back, of the Green's method approach to solving antennas. Okay? So it all trying to tie a bunch of disciplines together. I'm probably doing a lousy job, but simpler things. We don't have infinite slits. We truncate them. And so if I have a rectangular aperture, I'll have the same length B, and I'll have a width L. So now my I, it's nice because this rectangular aperture will be, L is perpendicular to B, so they're independent. So all those integrations, all the spherical wavefronts that add up in this direction are perpendicular from the ones that add up in that direction. So it's exactly the same analysis, just with twice as many integrals, but the integrals are exactly the same. And so we can write this, the intensity, as the product of B squared times L squared, my sinc function in S, and my sinc function in my perpendicular direction that looks like that. So beta is pi b over lambda sine theta, and gamma is pi L over lambda sine phi, perpendicular angle. So this slit here will give rise to a series of patterns that looks like this. So there'll be a sinc function in this direction and a sinc function in this direction. And notice that the B, or theta, will give rise to a more localized lobe than the narrower dimension lambda in this direction here. L rather gamma rather phi. So the tighter I constrain my aperture, the wider my diffraction is. The tighter I constrain my aperture, the wider my diffraction is. So if I take a look at the square window in the door behind you, and I flood it with light, it'll be a rectangular shadow as it goes off into, as it illuminates the room out the door. And that's because the dimensions of that aperture are so huge relative to the half micron wavelength of the light that there's no lambda over b to diffract. And so if I shrank that down so that it's now appreciably sized to a wavelength, then these secondary lobes kick in. Okay? So all is well with the world at the macroscopic scale as well as going down to the microscopic scale. If that aperture was illuminated by a couple of gigahertz, you can bet that there will be nice lobes on the other side of that. A more likely aperture is a pinhole. So if you want to build a camera, you can take a shoebox and you can cover the opening with foil and put a small little pin on a little pinhole right in the center of that foil, and then take out the bottom of the box and put just a screen, a piece of tracing paper, if anyone still remembers what tracing paper is. No? A very thin sheet of paper so that it acts as a screen. So now what you can do is you can use the spatial filtering of the pinhole to image exactly one set of scatterers off of all the scene that you're looking at, the trees, the mountains, and so on. And so you'll see just one angle projected onto that screen, and you have a very simple camera. A very simple and very robust camera with very, very sharp images. As long as you make that pinhole small, 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 you'll get a very, very sharp image. As you make that pinhole bigger, you'll make it more blurry. You'll violate the Rayleigh criteria. You'll allow too many sources to go through and pollute your scene at different angles. The bad news about that is you let no light in as you let your pinhole go down to 0. So your resolution goes perfect, but your light levels go way down. So at the back of that screen, instead of the tracing paper, you have to put a plate of film, and you have to sit that pinhole camera there for hours while the photosensitive gel reacts. And those are the very early cameras that came on the field in the early 1800s. Okay? And that's why some very interesting effects with these old screens. You'll see ghost images of people walking slowly through and not resolved very well. Of course, now you can do that on your cell phones with a panoramic view, right? So that's a sort of a pinhole camera. Now, if you want more light into it, you still need that pinhole, but you also need an array of lenses to funnel the light through at exactly the right angles. And so if you think in terms of a lens for a camera system, you're building off of that pinhole structure, but you're adding lenses in to let in more light, to shove more light through that pinhole at exactly the right angles so that you don't blur your image. Okay? A little bit of theory of, I don't know if anyone's an amateur photographer, but that's a little bit of the theory background for that. Anyway, the circular symmetry changes things enough that So when I add up all my point sources, when I do the integration, let's say this is b over 2 radius, and I do all my integrations around this, I have a sufficiently difficult integral that gives me a slightly different output. Out pops, because of this e to the I cosine of theta, d theta, this begins to look like an FM signal, and so we have Bessel functions that pop out of this particular integral. So J1 is the first Bessel function. But it looks similar to the sinc function, except the zeros are not evenly spaced. Okay? I think they get further apart as you get further away from the axis. Okay. Well, gee, one slit was so much fun that now we'll add two slits together. So I'll have some axis, and I'll offset a slit above and below, and I'll make each of these slits of aperture B. And I need to survey this in. So the distance from center to center of the slit I'll put as C. And then no, I'm sorry. I'll put that as D, so that from the origin to the center of the slit will be D over 2. And it turns out I have the same integral because I can imagine a slit being D plus B wide, and I'm just taking out the center of it. So my individual disturbances are exactly the same, but my limits of integration, when I go ahead and integrate, we'll be integrating from the bottom here to the top here. So D over 2 minus B over 2 to D over 2 plus B over 2. And remember, when I did this, I set up the situation where I was adding the ones from below and above. Now let's see if I can, let me draw you a bigger picture. And maybe I can do it here. In the far field, I'm going to have parallel lines that come out of each of these apertures. And this angle here is what we called theta before. If I use this guy here, so that these are perpendicular to those lines, then this angle here is theta, and this angle here is also theta. So this distance here is b sine theta. This distance here is d sine theta. And those two are my two basic phase shifts. So as I march my integration up from this point to this point, from this point to this point, I see relative phase shifts of b sine theta superimposed with relative phase shifts of d sine theta as I move those up. So if I do this integral, we get this. It's a fairly simple integral. Substitute in the lower and upper limits. We get those. And again, I have a sine of a minus b minus a sine of a plus b. I have a sine of a plus b minus a sine of a minus b. And so again, this is sine of b cosine of a. So u will equal twice ab times x times the sine beta over beta. That comes in play from this b. I have a new modulating term, cosine gamma, and then I have the sine of omega t minus kx. And the gamma, this b sine theta, gives me the beta, and d sine theta gives me the gamma. To be clearer, gamma is equal to pi times d over lambda times sine theta. Or the intensity is proportional to 4 amplitude squared sine squared beta over beta squared times cosine squared of gamma. So I have an additional modulation that comes about from that. So if I plot my sinc function, lousy. This is my sine squared beta over beta, and modulated underneath it, is the high frequency cosine of gamma. And this particular case was d is equal to 3b, or gamma is equal to 3 beta. So you have 3 lobes before you get down to 0. So what you actually see is this black line here. And you see that by using 2 slits, you potentially narrow your light distribution. So by having a single slit, we're able to get a distribution. By having multiple slits, we are on the right track of narrowing that distribution. Okay? So if I continue to make gamma finer and finer, I can spread these guys out even more. Or what I can do is increase the number of slits. And so now, off to an observation point, I have the interference from many of these slits. These slits still have a finite width. So my resultant field have some amplitude with some phase function here. So I'll have a slit at the center, and then I'll have slits out to n-1. You can look at this as just an FIR filter with different delays from each one of those openings, each one of those apertures. And this finite sum can be rewritten more compactly. So the intensity proportional to a squared, e to the I theta, e to the minus I theta equals a squared. Working through that, the intensity a squared times 1 minus the cosine of n delta. Notice the higher frequency modulation term of the n over the 1 minus cosine of delta of the denominator. And that can be rewritten in terms of sines, 1 minus the cosine in terms of sines. And the hard part is, what is delta? Well, our gamma is equal to delta over 2, which is pi d sine theta. That was the distance between adjacent slits. So the intensity is actually proportional to sine squared of n gamma, our same gamma that we had before, over sine squared of gamma. Now, this amplitude function here is our single slit, and that's our sine squared beta over beta. So this is proportional to some amplitude times sine squared beta over beta times sine squared of n gamma over sine squared of gamma. And if you plot this, you get very, very, very sharp spikes that repeat in time with beta. So you can pump up this modulation term. You can pump up this modulation term by adding lots and lots and lots of these slits, and that device is called a diffraction grating. And it's wildly, wildly popular in a lot of optics devices, photonic devices. And again, it forms a basis for an antenna with large numbers of apertures. So if I have many, 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 many apertures, I can squeeze down, get very, 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 very narrow beam modes, essentially as n goes. Okay?